Hello, welcome to the latest episode of Data Unchained. I'm your host, Molly Presley. Today, we're recording at the Supercomputing 24 or SC24 convention in Atlanta, Georgia. And as you can see, I think from the places behind me, bustling, busy show with a lot of excitement going on, not just in the supercomputing world, but enterprise HPC and AI architectures all kind of are converging. So without further ado, let me tell you a little bit about this podcast if you're new to the show. This show is all about how data has become increasingly distributed. It used to be that it was centered around the mainframe in a single building and all the applications and people were local to the data. And that's not the world we live in today. Now you're talking about multiple data centers, clouds, data being generated on sensors and at the edge. And that's created a lot of challenges around data architectures, but also a lot of opportunities for those who can overcome the difficulty of dealing with distributed data. So we have guests on our show who talk about both the challenges as well as the solutions that they've implemented in tackling this problem. So without further ado, we have a great guest with a lot of experience in this area, Chris Sullivan from Oregon State University. Welcome.
Thank you.
So Chris, before we jump into the meat of the show, maybe tell us a little bit about your background.
So I'm currently the Director of Research and Academic Computing for the College of Earth, Ocean, and Atmospheric Sciences at Oregon State University. I've been there 25 years. My wife and I both work there, and so we're both researchers. I do both research and administration, and so I hold grants, and I actually write papers and things like that. And so I'm really in tune with how technology affects our research.
Awesome, and I feel like it's a cool thing when we get folks like you on this show because you're a visionary, you're a user, you're looking at the industry trends and kind of bring all those pieces together.
Yeah, I really noticed that technology limits the way we can do science, and as we change technology, it removes those limits and removes bias and changes the scope of the work that we can do, which really adds to the scientific work.
Awesome. So at Oregon State, tell us a little bit about, maybe the university in general and what your group is doing.
Yeah, so my group's really focused in on climate change and dealing with the oceans, the atmosphere, and even the planet as a whole. And we're trying to understand how the way that we interact with it changes our environment and changes the world, and how we can create pathways to keep it the way we want it. And look at things like the carbon cycle and things like plankton that provide us half of the oxygen that we breathe on this planet. Or the plankton also provide like 17% of the food per capita on this planet. And if we start losing things like plankton, we will actually lose our ability to live on this planet. So, yeah.
So important problems.
I like to think they're important problems, yes.
So where does your data come from? I think, that if you think about the number of plankton, how do you know things like that? Where do your data sets come from?
Yeah, so my group's actually doing lots of AI work, generating camera data, sensor data. For example, the plankton work, I have 8K cameras that we bring through the ocean, and we're able to actually film the ocean. I'm able to segment that and identify billions of plankton on each run. I get about 100 terabytes of data every 10 days on that project, and we turn it into about 400 tera and then process it through. And it has to be processed through very timely, otherwise it's irrelevant. If it took me 6 months to get through that, I can't tell you what the oceans are doing right now, and we can't affect a change.
Right.
Yeah.
You need to have a little bit more of a real-time kind of situation.
Absolutely.
So you use a lot of computing power. Maybe tell us a little bit about your compute infrastructure.
We have a Center for Quantitative and Life Science. We have my infrastructures, and we're starting to bring them together because ultimately collaborations start to happen across domains and scientific domains. And so we have groups in my college that are working on all those different sensors, but we also have combinations of genomics happening and all these pieces. So that way we can actually understand the species that we're working with better. We have sound data. We have a lot of these collaborations, and we're really focused in on buying technologies that help us expand that. Mm-hmm. So, for example, processing and file space are probably the two major, and then network to tie those together. And those can present limits to how we can get through those data sets. It's about combining domains for us right now, so that way we get a more holistic picture about what's happening with our world.
Okay. And so when you come to a show like this conference we're at, Supercomputing, you're probably looking at what new technologies are out there, what's coming about. What are you looking to solve right now?
I mean, so right now we've recognized that there's a sustainability aspect to everything, and that as we keep trying to ramp up on technologies, we consume more and more power, and that requires more and more resources like cooling and data centers around that. And so what we really want to see are the ability to reinvent those spaces and reinvent the way that we're doing cooling and reinvent how we're deploying power. Because if we keep going the rate that we're going to suck up every bit of power in the whole known universe trying to do AI. And so we've recognized, and I've done some projects with NVIDIA to show that liquid cooling is extremely important to get back the performance and get back the sustainability aspects of using these types of technologies.
I think that's a really interesting point that you're focused on climate change, and certainly figuring out sustainable ways to do computing is something we're going to have to figure out as an industry for sure. When you think about the kinds of technologies you need to put in place, my perspective is we have a lot of technology that was designed for single data center, one environment, compute in a fairly small scale, and now we've tried to explode those out to work at this massive scale in a distributed world, and a lot of just inefficiency has come about in that.
And risk. So there's inefficiency and risk, okay? And so if I put everything into one container, essentially, that I have risks when there's problems around that container. And the risk is that if a single data center or something along those lines goes down, my processing stops. I have a project called the Ocean Observatory Initiative, and it's a 25-year funded project where we have data sensors giving us minute interval data coming from the Pacific Ocean all the way back to my data center. And if that gets turned off, we're going to lose that data. And so it's about gathering that data. Now, the most important thing for all of science is data. We kind of laugh when people say, I'm a data scientist. All scientists are data scientists. All scientists work with data, okay? And so data becomes the most paramount thing that we actually have. It's our commodity. It's what we live on. And so if I can't get the data and I have a risk associated to that data, then we lose the ability to do our science.
Absolutely. So maybe let's just kind of tackle things a few step by step. So you're always inventing new technologies and needing to adopt them. I know you've started to look at Hammerspace as some of the solution that you're going to go to there as far as technology obsolescence and moving to some newer things. How do you keep your workloads up and running as you go from older stuff to newer stuff and start moving around across locations?
And this is a good question, because this is one of the reasons we were looking at Hammerspace. It's been very difficult to migrate or transition from one, let's say, file space technology to another. And that's because as we keep migrating forward, everybody's got something new and they've done it in a new way. And I've got to completely migrate petabytes and petabytes and petabytes of data. And this is not conducive to getting more research done.
Exactly.
So it disrupts my research flows, disrupts my researchers, and it disrupts my ability to gather data. And so really one of the reasons we were looking at Hammerspace was their ability to treadmill new file space technologies on under a single name, global name file space, and let us treadmill off the old without impacting my users and without impacting any of the research. And that allows us to embrace any new technology that's coming out at the proper cost models that associate to doing good science, but not spending out billions of dollars, and actually focus in on science.
And I think that's ultimately what we're all trying to do. I mean, we're all here at this show and doing the work we do so scientists can create information, create new products, maybe some new pharmaceutical elements, right, whatever it is. So we want them productive. We don't want them twiddling their thumbs for a week while IT does some kind of systems work, right?
Yeah,
we want them to be continually working and accessing their data sets.
So downtime crushes our research capabilities. For example, the Center for Quantitative and Life Science helped create COVID Trace with the CDC and groups like this, and it's still being done to this day. If we stop COVID Trace, then the entire health community doesn't understand what's actually happening around our communities, and it affects us negatively. And so, yeah, that becomes paramount, that we're able to keep going with these services and the resources. That's a lot of the translational science that we're doing, is taking science that we've done basic science on, moving it to translational science and making it interact with the communities and the world around us.
So the idea of treadmilling on and off, I'm pretty sure you're not a marketing person, but I love that term.
No,
that's new to me, and I love it. It's a great visual.
Sorry.
So I love though you connect your users, your applications, your compute to a consistent namespace, and then let IT do what they need to do with their infrastructure.
Correct.
And
it actually creates a better relationship between my users and my IT, because they don't look at them as taking down their resource. They don't look at them as affecting their research negatively, and they've implement technologies that keep them moving. It creates a wonderful relationship.
So that's great. Let compute work, let researchers work. So let's talk a little bit about efficiency and all of that. So Hammerspace announced Tier 0. You provided a quote for the release, which was amazing.
Yeah.
Because I know you're excited about it. Maybe talk a little bit about why. We don't need to go into the marketing spiel, but when you see big inventions that are going to really make things more efficient and faster, that's exciting.
Yeah, so for us, we have a lot of HPC. I've got thousands and thousands and thousands of nodes. We've got thousands of users, and we've got petabytes of data. And so when we look at that, all the data that's in global file spaces or in mounted file spaces, users love using because it follows them around. But they're very poor at using scratch space on the nodes. And we have purchased the scratch space to help them go faster, but there's a different amount of scratch space on every node, a different type. And all of this combination creates a context where they just don't know how to use it properly. Mm-hmm. And Tier 0 allows us to overcome that problem, stitch the scratch space together and make it usable, but present it to the users in a way that they can use it, okay? And that, to me, is the win, because I will finally gain back the speeds that I intended to get by putting that scratch space there at a minimal cost of return, and ultimately, it's extremely sustainable. My goal is, again, sustainability, and sustainability is about, I've already got that hardware turned on. I'm already powering it. I'm already cooling it. So now I'm finally taking advantage of it in ways that I wasn't doing before.
And I think there's a couple angles there. And Tier 0, we only announced it 5 days ago. So every person I talk to, I'm learning a little new nugget. But you mentioned something there I thought was interesting, that idea of you can't control user behavior. They're not IT people, they're scientists.
Right.
And so being able to use their scratch like they've always wanted to, and you don't have to change their behavior, and it just automatically is much larger and also shared, is a big piece of just let them do the work the way they want to, and you now have a much larger scratch space to work with. That's I love that.
Yeah. Users love AutoMagical. Whatever we can do to lower the activation energy for them is really important. Mm-hmm. We've gone to the point where we compile all the software. We even have tools to launch the jobs for them, either from the command line or from the graphical environment. So they're really focused in on the science. And if any time the technology takes them away from that, that hurts us. And so that's our goal. And really, Tier 0 helps them keep focused on the science without having to think about the technology.
And then on the IT side, getting these server nodes up and running and burned in and configured and working, that takes time, but that's done now.
Yeah.
And so there's some beauty in, you can just put some software licensing in and turn on this capacity. It's a low barrier to entry for something that's already installed, right?
And it actually deploys us much faster, because every single time we deploy a machine with a different type of scratch space on it, then we have to do different things, and we have to prepare it in different ways for that workload. This is going to become more of a standard for us and allow us to say, hey, when you're buying these machines, let's buy this. It'll lock into the standard. You'll be able to use it. Mm-hmm. And that is more inviting to the researcher than saying, well, I need this. Just set this up for me one-off.
Right.
We don't have to have these one-off solutions anymore.
So that's really cool. And that talks about a lot of what's happening locally to your compute environment. Maybe talk about multi-site distributed environments. Are you working across hybrid cloud, or what does your distributed nature of your environment look like?
This is really important, because everybody right now is like, I need a bigger data center. I need to build a new data center. And my university was at that exact same point because of power and cooling. We recognize that so many of the data centers are becoming empty because the technology gets smaller but more power hungry.
Power dense,
and so we only have so much power and cooling in those rooms. As we bring in new technologies, they empty out racks and leave empty space. And so we recognize that it might be better and more sustainable to upgrade server rooms that we have to accommodate the cooling and power that we need, and then use them in a way to create resiliency within our networks and within our compute farms. And so that's how Hammerspace really stepped in for us, is that we were working with groups like Dell to actually do a test, and we did this, and we were able to show that we can run HPCs across multiple buildings, 4 buildings, for example, at 2 kilometers, doing full MPI jobs and farm jobs without any issue. What we really needed was a global named file space to go across those buildings, and do it in such a way that even if one building went down, the other buildings were not going to be affected, and the jobs in those buildings were not going to be affected, meaning all that other research was still going. And that's what Hammerspace has really provided to us. And that's why it was so crucial for us to start working with them, is it created resiliency within our HPC that didn't exist without it.
Yeah, and HPC wasn't originally really designed for resiliency, was it?
No, it actually was designed around, if a node goes down, that's fine. We can just
run the job again.
Run the job again. And that's great, but some of these jobs have a temporal aspect, like the plankton,
right?
Or COVID
trace, whatever
exactly.
it is.
And that if we're not able to publish that data in the time frame that it needs to be published, then there are issues for society and all these other pieces. And so we recognize that there's that risk, and that I keep coming back to that risk because we need to manage the risk a little bit better. Researchers haven't focused in on risk; they focused in on getting the work done, and the risk is always something that they put off to the end. We can now allow the IT groups to integrate risk management without affecting the researchers.
I love that. So it's kind of a multi-pronged strategy of things you're doing here to accelerate your science, your researchers at the node, across the data centers, built-in data protection, availability, all of that. That's correct. A great strategy. Just if words to the wise for others who are maybe just getting started on this journey, and I think there's a lot of folks who are used to either how their enterprise IT systems were built and they're not working real well in AI, or traditional HPC where it was kind of one big supercomputer and everything revolved around the supercomputer. Like, what are the steps to take to implement a more dynamic environment like you've built?
Well, so I mean, that's become more difficult as we went through time because we've not been training the upcoming generations about hardware. And that hardware knowledge needs to be incorporated into our educational process back again, so that way we can more easily teach people how to onboard these technologies. That's a barrier that we need to overcome. People like myself who had all of that in the past are able to still leverage it, but at some point, that's going to diminish as well. And so when right now I'm in the active process of training our students how to create HPCs, what that context is, just teach them about the networks in the file space. Everybody knows a little bit about processing. Most of the upcoming students and most of the groups, people coming forward, don't understand RAID volumes and don't understand, how to really scale data and how to really interact with data and how to protect it from ransomware and all these different things, or how to deploy a network such that the data can be moved around those networks in an efficient manner. And that needs to be there for us to actually work together and for us to be successful with data.
I've been in this industry for a long time, so have you, and there was the waning interest in HPC, right? There was a worry about the skill sets and everything that we as an industry were having conversations 10 years ago about how do you get academia interested and students interested in those programs. And this rise of AI has really helped with that, right? There's a career path that people can get really excited about as they're going into university of, I want to do this because I want to be in AI. So there's a lot of renewed interest, I think
there's also a tangible return for all of them to now see, I did this and the society gets this back.
Right.
In the past, it was much harder for a lot of the computer science people who wrote some little piece of a code to see how that code really changed the world or impacted things. With AI, they can directly see the impact and they can follow how that's affecting and upgrade it and make it better and better as we go forward. So
absolutely.
I do agree with you. There was a desert on HPC, and people thought that we were going to be able to just collapse into machines with high thread count. And I never believed that. I had been doing HPC since the 1990s and also heterogeneous HPC. I mean, in the end, we had collapsed down into just one architecture, x86. And that was actually limiting because in the end, no chef would walk into a kitchen with one knife. Okay, what kind of a meal are you going to get, right? And so I want multi-architecture because I want to be able to put the right type of research work on the right type of equipment and know that the data is going to go through it beautifully.
Yeah, absolutely. I could talk to you for hours. There's so many things in my head to talk about, but I think that's great for today. Thank you for joining the show and for sharing some of your insights even on some of the new technologies that are just really coming out this week. It's been great having you. Thanks for listening to Data Unchained, powered by Hammerspace. To learn more, visit hammerspace.com. If you have a guest you would like to hear on the show, email me at molly@hammerspace.com.